Okay, all right, so this again overall is what we're going to be trying to answer in this semester, okay? Okay, all right. I see confused looks. Is this no? No? Okay. Okay, all right, so I'll have to work on that. This is the second slide in my slideshow. I found it, so that's good that it's still there, okay? All right, so again, this entire chapter is going to deal with the rate of chemical reactions, okay? A really good example of how reactions and rates can be affected by various factors is given here, okay? So has anyone ever tried to trap a lizard? How do you trap a lizard, besides just running around with the cage? What's a very easy way to trap it? So one thing you could do is you could pour very cold water on lizards. What happens to them? They freeze up, right? They paralyze, essentially. They don't necessarily freeze, but the problem with lizards is they are what are called ectotherms, okay? Ectotherms are organisms that cannot control their temperature, right? Humans are not ectotherms. We have a lot of different ways that we can control our internal temperature. Lizards cannot, okay? So because of that, their temperature is essentially just going to be the temperature of the surroundings, okay? So if you throw a bunch of cold water on a lizard, it's going to be that exact same temperature as the cold water that you threw on it, so about 4 degrees Celsius, okay? The problem with that, though, is that there are all these little chemical reactions that are taking place in this lizard's body, okay? So these chemical reactions could be the actual muscle contraction for movement, right? If we cool those reactions down, the speed at which they occur is going to slow down as well, because temperature is one of these factors that control the rates of reactions, okay? So if we slow this rate down, or slow the rate of muscle contraction in the lizard down to such a temperature, such a degree that it can't move, that's essentially what happens when we throw water on them. They don't necessarily paralyze, but essentially, again, the rate of that reaction, the rate of the muscle contraction slows down with the cold water, and therefore it cannot move, okay? How can it go ahead and move? What needs to happen to kind of resuscitate it? Little heat, right? So a little sun shines down on it, it gets out of the water, if someone moves it out of the water, it's going to warm right back up, right? The temperature of it is going to warm up, as well as the temperature of those chemical reactions. They're going to speed up, and finally, it can move because of that, okay? All right, so temperature is one of these factors that controls what we're going to call the speed of a chemical reaction, okay? Another word for this is either reaction rate or frequently what I will call rate of a reaction. So rate of a reaction, reaction rate, and speed are all synonymous in my vocabulary, okay? That is ugly. Fix it. All right. Okay, so temperature is one of those things that affects the rate of a reaction. We're going to talk a little bit about why, okay? So kind of the assumption that we have with things reacting or molecules reacting is they have to collide, right? If you had a molecule out here and you had a molecule out here and they're supposed to do something with respect to one another, if they never come close together, then they're never actually going to react, okay? So to get them to actually react, they have to hit each other, and a lot of times they have to hit each other in a certain orientation, okay? So let's say we do have a collection of molecules floating around. If we increase the temperature of those molecules, what's going to happen to them? They're going to move faster, right? They're also going to have more energy associated with them, okay? So if they move faster, what's that going to do to the number of collisions they have per unit time? It's going to increase it, right? So if we increase the temperature, they're going to move faster, they're going to collide more often, we get an increased rate, okay? Another thing that affects this is concentration, right? So concentration, if we have more of something, right, what's that going to do to the overall amount of collisions that you actually see? Is that going to increase it or is it going to decrease it? It's going to increase it, right? The more stuff we have, the more chance there is that they're going to collide, they're going to react, we're going to see an increased reaction rate, okay? So concentration is also very important with respect to influencing reaction rates, okay? A couple of other things. Number 3, the presence of a catalyst. What is a catalyst? Does anyone know what that means? Yeah, so a catalyst speeds up a reaction. Speeds up reaction, right? And we'll talk about why in the middle of this chapter. And then the fourth thing is the physical state of reactants, okay? So let's imagine that you have reactants and there's some solid piece of metal, right? Some solid piece of metal that you have in your car, let's say, okay? And this is one of our reactants, our little solid piece of metal, and colliding with it is our other reactant. Let's just imagine there's some sort of gas molecules, okay? So you have the solid piece of metal, you have these gas molecules going over the top of it, okay? Now compare that to just a bunch of gas molecules floating around in random space. Who do you think's got a better chance at collision? The gas molecule hitting a solid surface, or the gas molecule randomly finding another gas molecule, colliding and having a reaction? Right, so the solid surface, we have a much larger chance of a collision, and so because of that, physical state of our reactants is going to be very important in affecting the overall reaction rate, okay? And again, we will spend a lot more time looking at all of these factors as we go through the chapter. Okay, so again, reaction rates, what are we dealing with? We're dealing with speeds of things, right? Okay, so if we go back to just driving outdoors, how do we normally measure the speed when we're trying to think in terms of our car? What does the nice little speedometer tell you? Miles per hour. So that's like, looking for the everyday thing, not kilometers, but miles per hour, unfortunately, because we live in the United States, right? What is a miles per hour? What are we measuring? What's on top? We're looking at a change, right? We're looking at a change in distance, right? And that per hour, what is it over? So we change in distance. This is our miles. And it's on top of a change in time. Okay, so we're looking at a change in distance per unit time. So does everyone remember what this guy means? This little triangle? Change, right? So we're looking at this Greek letter delta. This is change in, just as a reminder. And how do we measure that frequently? Is it like the middle state or is it a final state? So change in is always a final state minus an initial state, okay? And so we look at that with respect to driving, all right? So miles per hour is how we measure speed with respect to our car. What would be analogous in a chemical reaction? Because that's what we're going to be interested in, right? Measuring these speeds or these rates of chemical reactions. Do we measure how far a molecule is going to travel with respect to measuring reaction rates? What do we measure in chemical reactions? If I have a hydrogen and I have an iodine, what are these? The reactants, but specifically, let's say I just have one hydrogen. What do I call that? Just a molecule, right? So with chemistry and with chemical reactions, we're dealing with molecules, right? So we have a molecule, it's late, molecule, going to make another molecule, right? So with chemical reactions, we're not going to be looking at how fast something goes. We're going to be looking instead of how many molecules form and how many molecules do we use, okay? Now thinking about this, though, in terms of molecules, how easy would it be to measure molecules? Can we measure molecules without like a STM machine or anything like that? No. So molecules are super small. We can't actually measure them. We can't get a little magnifying glass and look at how many molecules there are. What do we usually measure these guys in terms of? On a bigger level. On the mole level, right? So we're usually looking at moles of things, okay? Moles of reactants, moles of products. But with respect to chemical reactions, do you think it's going to be super easy to go from, let's say, a mass of something and have it react with another mass of something when they're never in the air and they're never able to collide? It's not, okay? So with respect to mole, we can go from moles to things that we can measure, which is grams, but the problem with that is that it's not going to really apply here. What is another means by which we measure the amount there is in, let's say, a solution? Molarity, right? So molarity is a measure of what? Moles per liter, concentration of our reactants, okay? So with respect to chemistry, we want to know how many molecules of reactants are being used. We want to know how many moles of products are being formed, but we can't actually count individual molecules. We can't really count this in terms of grams, but what we frequently will count it in terms of is concentration, changes in concentration, okay? So, just as a reminder, molarity is how we frequently measure concentration, and it is defined as moles per liter. And that is moles of solute per liters of solution, okay? What is the unit for molarity? Unit, it can't just be moles per liter, but it has its own special unit, right? Just a nice capital M, super easy. And another way that we will denote this, especially with respect to kinetics, is we will denote it via brackets, okay? So brackets, if there's some sort of reactant in here, is denoting that this is a concentration of something, and that's going to be in units of molarity. Okay, so rates of reactions. How do we measure the rate of a reaction? So it depends, okay? It depends on what we're actually looking at. So we're going to be measuring changes in concentrations of things, okay? Now let's imagine that we have this reaction taking place where we have hydrogen and iodide reacting to form HI, okay? Let's say that we start at time 0 and we have, let's say, 1 molar of hydrogen, and iodine, we have also 1 molar of that, okay? What's going to happen, so we don't have any product, we only have 2 reactants. What's going to happen as we start this reaction? It's going to go, right? So reaction's going to go. They're going to go to make products. What's going to happen to their overall concentration? It's going to decrease, right? Because we're using them up to make our product. So let's say we come back, and let's say at time 10 seconds, we measure the concentration again of both hydrogen and iodine. And let's say it's gone down to 0.6 molar and 0.6 molar, okay? How would we utilize this data to measure the rate of disappearance of either of these two, okay? So we have our time initial at 0 seconds. We have our time final at 10 seconds. We have our initial concentration of 1 molar. We have our final concentration of 0.6 molar. Okay, so we're going to plug these in to measure how the rate of, let's say, hydrogen concentration changes over that time frame. Okay, so go ahead and say rate is equal to change in hydrogen. So who am I going to put first when I'm looking at this delta H2 over delta T? Do I put the 1 molar first, or do I put the 0.6? 0.6, right? So go ahead and plug that guy in. 0.6. Who is final? Who's my final concentration? Or initial, pardon me. 1, right? So minus 1 molar. What was my final time? 10 seconds minus initial time, which was 0 seconds. What is the problem with this right now? What is it? Well, we'll stick with the seconds because we'll frequently measure these rates in terms of molarity per second. What is the overall sign of this? It's going to be a negative number, right? Anytime we deal with a reactant, because the concentration over time is going to decrease, we're always going to be left with this negative rate of change, okay? So to counteract that, because we don't want to deal with negative numbers, we always want positive numbers. When we're essentially determining the rate in terms of a reactant, we will put a negative in front of it to make the overall rate positive, okay? So when I'm actually measuring this rate of reaction, I'm going to put a minus in front of whatever I get from this guy over 10 minus 0. That's really ugly, and that will give me an overall positive something, and I actually don't know what it is. So let's just be happy. 0.6 minus 1 divided by 10 gives me a positive 0.04 tenth 1. Okay, so let's say that these guys were molarities and our times were seconds. What is my units with respect to rate here? So what's on top? Concentration, right? So we have a capital M, molarity, and then what is it being divided by? Second, right? So all rates are measured in terms of molarity per second, okay? Okay, so that is reactance. That's good. So now we can determine the rate of reaction in terms of reactance. I think I went over too many things on this slide. I did. Okay. What about products? Okay. So with respect to reaction rates, we can pick any of the things, right? We could have picked hydrogen, we could have picked iodine, we could have picked our product, HI, to measure the overall rate of reaction, because again, they're all related to one another. If we're losing H2, we're gaining HI, vice versa, okay? Now, with these guys, with our two reactants, we had to put a negative in front to account for the overall negative sign. What's going to happen, though, with respect to the products? As time goes on, let's say we initially start, again, at time 0, and we're looking at our products, how much product are we going to have? 0, right? As we move on to time 10, what's going to happen to the concentration of products? It's going to increase, right? It's going to go from 0 to something, okay? So when we look at this overall rate of HI formation over time, is this going to be a positive or a negative number as is? It's going to be a positive number, okay? So we don't have to put a negative when we're actually measuring the rate with respect to a product, because overall the magnitude is going to be positive, okay? Now there is one more thing that we have to consider. So for hydrogen and iodide, there's a nice little 1 in front of both of these guys, right? What is the number in front of HI? 2, right? So let's say we only have 1 molecule of hydrogen, 1 molecule of iodine. How many molecules of HI do they make? So we have 1 and 1. How many HIs do I get? 2, right? So for every 1 hydrogen I use, I get 2 HIs. If I use 2 hydrogens, how many HIs do I get? 4, right? If I use 3, I get 6. So how is the relationship, because of this 2 in front, and because these guys both have 1s in front, what is that relationship between rate and stoichiometry? 1 to 2, right? And that goes back to the numbers in front of our balanced chemical equation. This is a problem. HI is going to essentially form at twice the rate that our 2 reactants are going to disappear at, okay? We don't want to measure different rates for different things. We want to kind of have just overall a nice solid rate that we can relate back later on when we look at the balanced chemical equation, okay? So because of that, what we will do is put a 1/2 in front of the relative rate of change of the concentration of HI, because, again, this guy is essentially increasing at twice the rate that the reactants are decreasing at, okay? So what we're going to do long term is, dependent on whatever this number is in front of our chemicals, we're always going to have 1 over that number in front of the relative rate of change of whatever we're looking at. And I will summarize this in a nice slide in a second, okay? Okay, so a couple more things. It gets kind of hot in here. All right, so let's say that we have a plot of both our hydrogen and our product HI. So I'm going to go ahead and rewrite my reaction here. I have H2 plus I2 going to make 2 HI, okay? All right, so I'm actually monitoring the concentration of H2 as well as I2 as a function of time. And I have right now a green line that refers to one of them and a red line that refers to the other. Which one is green, the reactant or the product? And how do you know? The reactant, right? How do you know that this green one is our reactant? It's decreasing, right? So that's a big hint that you're dealing with a reactant because the concentration starts at 1 and goes to approximately 0, okay? Then what's the red? Our product. And again, why is it our product? How do we know? It starts at 0 and it goes to whatever it goes to, something greater than 0, okay? How could you also figure out the stoichiometry of this reaction just by looking at this plot? So if you notice, H2 starts at, if I can zoom in here, starts at approximately 1 molar. Where does it go to? So green goes, we're approaching what? 0, right? So that's our H2. Now our product starts at 0, and where does it go to approximately? 2, right? So in the same time frame, our reactant lost 1 molar, our product gained 2 molar. That should be a very big indicator that this is a 1 to 2 relationship with respect to stoichiometry. The product doubled essentially as the reactant just fell off, okay? Okay, so a couple of other things. As we look at this, so let's say that we're just going to look at the rate of the reaction in terms of our product, HI, which is the red line, okay? So if we wanted to measure our average rate of a reaction, which is what we've been looking at, we could pick any 2 points on this little curve, right? So let's say I wanted to pick this point and measure the average rate between these 2 time points, okay? What would that kind of manifest itself as with respect to this curve? All right, so what I'm looking at here is trying to measure this, okay? If we're looking at something like the slope of this line, how would you measure the slope of this line? What is slope? It's rise over run, right? So rise over run. In terms of this plot, what is the rise? Right, so we have concentration or change in concentration over what? Change in time. What is this? Change in concentration over change in time? This is the reaction rate. This is the average reaction rate between these 2 points, okay? So compare this guy, fairly steep, to the same exact thing out here. What's happened to the steepness of this slope of this line? Right, it's decreased, right? Here, we're very steep, which means we have a very fast reaction rate. Out here, we're very shallow, we're not as steep. There's not as much rise over run, so the reaction rate has decreased. And you can look at that by just looking at, essentially, these slopes of these various lines between 2 points, okay? All right, so at the beginning of the reaction, it was fast. As we've gone through the reaction, it gets slower. And again, you can compare that via the steepness of these slopes. Why do you think that is? I guess it would be better to have compared the reactants, so very steep to not so steep, right? Why do you think those rates have slowed down?
There's less to react.
Right, there's less to react, right? As we've started, we had lots of things, they were colliding, they're hitting each other. As the reaction proceeds, what's happening to the concentration of the reactants? Decreasing, right? So now there's less to collide, there's less to react, and so because of that, we see this reaction rate overall slow down, okay? Okay, so a couple more things with respect to this. This is confused. All right, so these average rates are what we're looking at with respect to the change in concentration between 2 points, right? So if I wanted to take the average rate of reaction, I could measure this rate here, right? I could also measure this rate here. I can measure at any point in time along the curve, okay? That's a fairly decent approximation of what the rate is at that particular point in time, right? Well, let's say I picked this point, and as this is my initial point, and I picked this point as my final point. What would that approximate? So we would be looking at a line that looked like this, right? Is that a decent approximation to any point in time along this curve? No, right? So the closer we get with respect to measuring these rates, with respect to these types of curves, the better it's going to be an actual approximation of the reaction rate at that particular point in time, okay? The farther we get out, the farther we move away from one another with respect to the time points, the less good the approximation is going to be to the actual rate of the reaction, okay? Okay, all right. So, another thing, because I don't explain things well. So again, if I took this time point and this time point, wasn't a good approximation, right? Didn't measure the rate very well. If I took this time point and this time point, so this guy and this guy, it got a lot better. If I get this time point and this time point, it got a lot better, right? What could I do to essentially decrease that difference so much that I got the actual rate at what particular point that I wanted to measure it at? What is that called? Decreasing that difference in t, or that change in t? Right. Exactly. So taking the derivative of this curve at any point in time is actually measuring the instantaneous rate at whatever point in time we're interested in, okay? Kind of gone over this. So again, as the reaction goes on, we see these rates decrease. The big idea behind this, we run out of stuff to react. This will continue to happen. Do you think it will continue to happen forever? Just continuously decrease? It could, right? It could just run out of stuff, and so then it just go to zero, or more importantly, what we will frequently have happen is we will reach equilibrium, and we'll talk about kind of the implications behind that. So, next chapter, okay? Okay, so we were just talking about the average rate of a reaction, okay? That was picking two time points, taking the concentration, and the change in time between the two, and using that to approximate our rate between those two time points, right? What would be a better thing to do if we wanted to know the actual rate at one particular time point? So if we go back, does everyone know what derivative is? Tangent line to the curve, right? So what we mean by instantaneous rate is saying I pick this point. I want to know what is the rate of reaction directly at this point, not between any 2 points. To find that, I would take a tangent line to that curve, okay, at that point, and what would I measure? What would that tangent line, if I wanted a rate, what would I measure with respect to that tangent line? So I wanted a rate. Again, a rate is something to do with the slope, right? I drew this guy, and I wanted to know the rate at this point in time. I would take the slope of that line, right? That's what a derivative is. It's a slope of a line that is tangent to whatever curve you want to do, okay? So again, if I wanted the instantaneous rate, which is different than the average rate, I would look at the change in concentration over change in time with a tangent line that directly picks or directly is tangent to whatever time frame I'm actually looking at, okay? You don't have to know this, right? We never have you take instantaneous rates, but just note that there is a difference between the instantaneous rate and the average rate, okay? Okay, all right, so we'll leave that there. Okay, so we'll go ahead and we'll move on. So overall, in general, just kind of summarizing this section, when we want to measure the rate of reaction, okay, we have a reaction, we want to measure the rate of it. To be able to do so, we have to be able to measure the change in concentration as a function of time, of any of the things, right? If I can measure the change in concentration of hydrogen as a function of time, can I determine all of the other parts of the equation from that? Yes, I can, because I know hydrogen is a reactant, right? I know HI is a product, and I know that this guy is going to essentially double or increase at twice the rate that this guy is going to decrease because of the stoichiometry of the reaction, okay? So in general, if you have a reaction with reactants and products, if you want to measure the rate of that reaction, it's always going to be minus for our reactants, and then 1 over whatever number is in front of our reactant. Same thing for product, 1 over the stoichiometric coefficient for the product, okay? So I know this is a lot, but I'm going to go ahead and do an example to try to illustrate how you guys would use this, and then I'll let you do a problem with respect to that, okay? So we have a reaction where we have 3 different reactants, and they're going to make 2 different products, okay? And we know that in the first 10 seconds, the concentration of iodide dropped from 1 molar to 0.868 molar, okay? So now, the first question in this is, how is the rate at which iodide disappears related to the rate at which water appears, okay? So to answer this, I'm going to go back to that little expression that we just had, okay? So the rate of a reaction in terms of the disappearance of iodide, how would I measure the rate of reaction with respect to iodide? Iodide is a reactant, right? So what would I put in front? A negative. And then I have to put 1 over whatever the coefficient is. So what is the coefficient in front of iodide? 1 over 3. And then change in concentration of I over change in time. Okay? This is equal to the same exact thing for water with respect to whatever is in front of water, right? So is water a product or a reactant? It's a product, so I'm going to go ahead and put a plus. 1 over, what is the number in front of water? 1 over 2. Change in concentration of water over change in time, okay? So what they want to know is, how does this guy, the relative rate of appearance of water, relate to this guy, the disappearance of iodide, right? So there's a 1/3 and there's a 1/2. So what I'm going to do is I'm going to isolate this guy by itself, okay? How would I do that? I would multiply both sides by 2, okay? This is going to give me 2/3 the relative rate of disappearance of iodide, and I can go ahead and put a negative in front, is equal to the rate of appearance of water, okay? So this is what they mean by rate at which water appears. How is it related to the rate at which iodide disappears? What is this number in front? 2/3, right? So the rate of water appearance is 2/3 the rate of iodide disappearance, okay? And again, we can get that just from the rate expression by itself. You could also try to figure that out in your mind by saying, oh, there's 3 of these and there's 2 of these, so it's 2/3, right? But again, rate of appearance of water is 2/3 the rate of disappearance of iodide, okay? All right, so then B, they want to calculate the average rate of the reaction in this time interval, okay? So now we're going to go back to this guy, because this is what we're actually interested in, the average rate of a reaction. Who are we measuring, again? Who do we actually have data over? The iodide, right? So if we want the rate of a reaction, we're going to be measuring our reactant again. So we're going to be measuring our iodide. We're going to put a negative in front to account for the negative. And then again, we're going to include this 1/3 because of the 3 in front. And we want to have just an overall nice rate in terms of one molecule that's being made or used, okay? So 1/3 delta I minus over delta T. So we actually have this, so we have 1/3 the change in the concentration of iodide. So what is the initial concentration of iodide? It's 1. What is the final concentration? 0.868 molar minus the initial concentration, which is 1. And again, that's in terms of molarity, divided by, what can we infer about the time? Starts at 0, and then what does it go to? 10 seconds, right? So you can put this as 10 minus 0, or just 10 on bottom, okay? All right, so once I have my numbers put in, I can go ahead and just calculate the rate, which I think I've done. Maybe not. I should have. It'd be dumb if I didn't. Okay, and we get a number that is positive 0.0044. And again, what are my units here with respect to rate? I have an m over a what? Seconds. So molarity per second. Okay, so then this last little bit, they want us to determine the relative rate of change of the concentration of protons, of H+. Okay, so I'm going to go ahead, slide this guy down. So right now, we know the rate of the reaction, right? As long as we know that, and we know the stoichiometry, we can figure out the rate of change of any of our reactants or products, okay? So we're going to go back to that rate expression, but now in terms of protons. So rate is equal to H+. Is this a reactant or a product? H+ is here. It's a reactant. So we're going to put a negative in front. 1 over 2, because of the 2 in front of the H+, delta H+ over delta T. This is what they want. When they ask the rate of change of H+ concentration, that's what they're asking for, right? We have the 1/2. Do we know the rate of the reaction? Yes. Where do we get that from? B, right? So B gave us this guy. So we can go ahead and plug that in. 0.0044 is equal to minus 1/2 delta H2, or H+, pardon me, too many hydrogens today, over delta T. We can treat this as its own little algebraic quantity. How would I solve for delta H+ over delta T? I would just multiply both sides by 2, right, to isolate it. So therefore,
so why just 2 and not negative 2?
Because, okay, we'll do negative 2, okay? Because the whole idea is, like, they're looking for the rate of change, right? We know that it's disappearing. It's going to be a negative because it's disappearing. But if we're asking for, like, the disappearance, sometimes the words get they're kind of a moot point. But we'll go ahead and say minus negative 2, or multiplied by, pardon me, negative 2. So we get a delta, make this prettier, delta H+ over delta T is equal to a minus 0.0088 molar per second. So again, they're asking, how does proton, what is the change in concentration of proton? That is it, right? It is 0.0088 molar per second, whereas the average rate of reaction is 0.0044. Okay, all right. So we have not very much time left, okay? So we'll go ahead and do one thing. We'll go ahead and do this problem, question 14.1. I think I only want you to answer the A part. So I just want you to calculate the average rate of the reaction during the time interval that I give you data for. So we're measuring HBr, measure the first 25 seconds, and I tell you how the concentration changes. I think I instruct you to include units in your answer. I can't quite remember if I do or not. ahead and have you guys sign in on this little sign-in sheet. Just write your name semi-legibly so that I don't withdraw you on accident. Also, consider significant figures. That's an important thing, too. Make sure you sign the sign-in sheet, and I'll just tell you, there should be 2 sig figs in the answers, or 2 significant figures. Okay, so we'll go ahead and pick back up with this when we come back on Thursday. Ideally for A, you should have gotten a rate of 0.0018 molar per second. It was 0.00176, but you should round.